Hello, everybody. We will probably spend 1 more minute or two to wait for everybody to get on board, and then we'll start. Meanwhile, I will tell you a few things about myself. So for those of you who don't know me, my name is Ciprian Tibea. I'm the country manager for Baltics, Romania, and the rest of the world. I have quite a few experience, a few years in finance elements. And a few words about our company and our products. So our company, StruSoft, has a lot of software. I will remind just a few of them: FEM Design, Prestress, and Impact. And lately, we have developed a new family of software called the Simplex family. And the first software in this new lineup is the Beam software. And I encourage you all to have a sneak peek and a really nice presentation tomorrow. So you can register for the webinar that will happen tomorrow that will have the main focus, Simplex Beam. All right. And then for today's webinar, I have brainstormed what to show you guys. And I had quite an interesting call with one of your fellow engineers. And I realized that there are a lot of things that I haven't considered telling you before, and that are really important for you guys in day-to-day design. So the first topic that I want to touch in this webinar is how to create stirrups for topping and beam. And I got this question quite a few times in regards to how you place stirrups that go from the beam in the topping, and I will show you just that. Then the recessed beam design and what is the logic behind it, because if you try to play with it, most likely you've got some errors about faulty support position, and you didn't know why. And we will go through the design of the recessed beam, and everything will make sense afterwards. Then some tips in regards to view options. Then we will take a look at the sloped beam, and I will give you some tips on how to create your custom sections. So for example, if you want to go from a rectangle to an I section, or you just want to have an I section all the way, or a T section, we will go through that. Then a hollow core slab, and if we have time at the end, we can design, a beam or a hollow core, depending what most of you will want from start to finish. What I want to say is the last point in this agenda is the Q&A. So please feel free to ask questions during the webinar by text. You have a question tab, and after the webinar, we will answer all the questions and send you the responses via email. Okay, so without further ado, it's not thank you for your attention yet. I have created this project, which basically consists of a rectangular beam, as you see here, that has a topping, and we will see how to create those stirrups, some of them that are only in the beam and some that go from the beam through protruding the topping. Okay, and the way we do that, let's do some default placing, right? And here at position, I have this drop-down menu, and I can select either beam or topping. So if I select topping, you see the stirrup has moved and is now going from the beam to the topping. And if I leave it like this, beam topping, and then I move this section viewer, I see that in the middle part, it goes in the topping, and then towards the side is just in the beam. So basically, this is how you create those stirrups. Now, let me open a new file. And take a look. Let's take this one. Okay, so we will move to the second topic in our agenda. Maybe we should do like this, the recessed beam design. And yeah, the way we do it, so in this case, we have a T-beam. But first of all, I want you to have a look on the position of the supports. So you see that the position of the supports is moving, starting from the release phase, where the position is at the start and end points of the beam, and then moving to storage, maturing, transport, and then moving to the site where you place the element in the building. The position is changing, and therefore we have to keep this in mind, because when we will design our recessed beam, we have to take into consideration this support position. So for example, if I go in, let's say, transport, and I want to see the position of this support, I see that the support position is 0.6 meter inwards, right? And then if I move it to the final stage, 6.1A, and I go again to the support, I see that it's just 60 millimeters inwards. So we have to have this in mind, the position of the support. Okay, because it is connected, and that's why it might cause quite a few issues, and it did cause a few issues for myself as well, as I had to research and understand what's happening the first time that I design it. So yeah, let's calculate this and then move to the recessed beam. So in order for you to reach the design part of the recessed beam, you have to calculate your beam in the first place. And then by using tools and recessed beam, you can design the recessed part. So now we are in final stage. Let's go in final stage A. So in final stage A, this was already calculated. So I will explain to you the logic of filling in those numbers. So this is the cutout zone, LR and HR. Then the delta is the distance from the start of the cutout to the half of the plate, to the beginning of the plate, sorry. And then LP is basically the size of your plate, which is right in the middle, is the support position. So having in mind that our support was 60 centimeter, 60 centimeters inwards, sorry, 60 millimeters, then we have made the LP 120. Then if I remove from the LR LP, the result is this delta. So yeah, and the WP is the size in the other direction. So yeah. All right. Then this is the thickness, and then all the other values are like reinforcement, which are going to be highlighted as soon as you mouse over them. So that's why I told you that it's really important to know the position of your supports. If I go into transport, you see it says the input is faulty. And why is that happening? Well, it's because my support is, instead of 60, is at 600 millimeters inwards. So we can fix that as well. For example, if we make like a bigger cutout, right? So we make a cutout of, I don't know, 1000 or 800 millimeters. And then we know that the LP should be, we need more, 10 times bigger. So yeah, 400. Okay. And the delta should be 200. And now it works, right? Because I had in mind this position of the support. Of course, you can make the plate smaller. Here you get some indications about the required plate dimensions. You can also play with this chamfer zone. You can either do it like a straight corner, or in our case is a straight corner, even though it shows that it's chamfered. But you can do it like a chamfered zone, just inserting here a value. Yeah, basically that's the trick with this recessed beam design, to have in mind the position of your support. All right. I'm pretty sure that there are questions related to this, and I don't know if I was clear enough, but yeah, if you have questions, ask them, and yeah, you will receive your answer afterwards, or we can even make a one-on-one call at some point. Tips in regards the view option. Oh yeah, okay. So if I go for example in this final stage 6.1a, and if I go to options, I can either select just the section, and then I have an overview of what's the section of my beam, or I can go into detailed view if I want to see like a lateral view of my beam with reinforcements. So I don't know how many of you actually use this. It might be helpful in some cases. So yeah, now you know. All right, next one is the sloped I or T beam, and tips how to create your custom sections easy. Let's open a new file, and let's go with the big beam, and we select an I beam. Now, if I click configure, I wake up with this new window that at first glance might look scary, but it's actually not. So what can we do about it? So in this current setup, it starts, as you can see, from a rectangular section. It goes up till this point, then it has a transition area, and it transitions from a rectangle to an eye section, where our heart thickness is a little slimmer, and then the heart goes like a bulkier. So this is the drawing, what it says. Now I also have two sections, 1.1 and 2.2. If I click the sections, I end up seeing this new window where I need to fill in the input data. So for example, now I have an eye section, but what if I want to create directly without going and changing to a sloped I-beam? I can easily do that by just modifying the size, and now it's a T, as you can see here in the middle. But I also need to modify those. So again, it's a T. Now, what if I want to have a T-beam, this beam, starting from the initial position without having this rectangular section? So that is also achievable quite easy. I can go here and delete this one, or actually not delete, place it as a 0, 0, and then 17,100. And now, basically, it has no dimensions. So even though you are looking at the cross section, you see that it has no dimension, the rectangular one. And if you look at the top view, you see that it's just a line. So basically, our beam is now a sloped T-beam with a T section, a variable T section from start to finish. And this is the way how you can customize your beam, sloped I-beam. Now, in the same principle, I can play with all the dimensions here. I can extend this transition zone. I can make, like, as I said, a slimmer heart, then increase it, or whatever I want with it. And this is like the better approach compared to using custom sections. And it works in the same manner if you get like the T-beam, the sloped T-beam. So yeah, I hope it was clear. Of course, all the dimensions can be modified here, so you can get to your desired section. Okay, let's see what we have on agenda next. HoloCourse Lab, quick overview and design. Okay, so probably some of you are working with the HoloCourse Labs, and we can have a quick look on how to design a HoloCourse Lab. So let's take a standard one. This is too large. Yeah, probably this one might do the trick. All right, and we have the option to create or not a topping. Then we have the option to consider if whether our topping is just a leveling topping or a structural topping, meaning that you will have reinforcement and probably a bigger thickness in that layer. but for this example, we will keep it like this. All right. Oops. What happened? No idea. Sorry about that. Let's try to, maybe it was something with that section. Constant and okay. Yeah, now it works. I don't know what happened previously, but probably some user input failure from my side. So this is our holocore, as you can see. Now, the software automatically detects when you have a holocore, and you should click it like without shear reinforcement. I don't know why for this particular model it wasn't clicked. Anyway, that's why you should always check it. So holocores do not have stirrups, and therefore it's a different equation that's being used because the concrete takes all the shear force. All right, then moving back to our holocore, we can, you know, use a layer of reinforcement. We can even place, like, if we want, 2 bars at the top. Some of manufacturers do that, others don't, and then we can count the bars. It's like 1, 2, 3, 4, 5, 6, and 6 bars, 6 tendons at the bottom. And then we can, you know, inspect it like this and to see if whether the position is okay. Of course, we can make adjustments to the position by using the coordinate system X, Y, Z, and you have the representation of the X, Y, Z here in the longitudinal and transversal sections. Now, of course, as you probably saw in previous webinars, you can modify the pre-stressing force, you can modify the material of the tendons, you know, making new diameters and so on and so forth. So let's leave it like this for this example. And yeah, then, oh, sorry. One more thing worth mentioning here is the edit, recess, and core filling. So I told you in previous webinars as well, here you can fill in some of the cores, or you can make cutouts in your holocore easy. So it usually starts at 1, so it's 1, 2, 3, 4, 5. So if I click ID 1, start 0 and 1000, and click add, it basically filled in this core. If I move it, you will be able to see it with green, that okay, that core is now filled in with concrete. And in the same way, I can fill in the last core. And now I have symmetry throughout. The reason why I do this is usually to increase the shear force near the support area. Yeah, following the same principle, you do the cutout. So you give it like the starting coordinate, 1000, maybe make it 3000, so it can be more in the middle, and then 200, Z0, weight 150, height 265, length 150. And I have created a cutout, right? So yeah, this is how you do you know, core fillings and recesses in this holocore. Okay, Yeah, one additional thing, if you didn't participate in the webinar where we talked about creep and shrinkage, note that you can access our creep and shrinkage page by either, you know, do a quick Google search, creep and shrinkage StruSoft, and then let me show you. Out of concrete. Yeah. So it basically takes you to this page, which is free to use. And you just have to insert the input data and then click calculate. And if you want, you can even check the calculation made, copy it, place it in your notes. Yeah, so this is how you calculate creep and shrinkage. Now, probably you ask yourself, okay, but what do I do with this creep and shrinkage? Well, in that particular webinar, I showed even differences between using and not using creep and shrinkage. But you have a table here. Basically, you fill in the creep and shrinkage data, and then you perform your analysis in a correct way with regards to creep and shrinkage. Yeah, so here I have at the moment just one load case. So normally if I want to take this design to the end, I should create more load cases. So here in this input loads, load cases, I can define, you know, whatever loads I want and load cases, sorry, and add them. So, yeah. And from this menu, drop-down menu, I select which load case is active, right? And then if I click this one and I go release phase, of course, we don't have any extra load in release, neither we do in, you know, transport or, yeah. Maybe we have some loads in this intermediate stage, maybe some permanent loads. And here you have like the tab where you can add the type of load that you have, like uniform, trapezoidal, point load, etc. So yeah, you can do that quite easy. You can even check if whether you know, you have an eccentricity in your load. Then of course you will get a torsional moment and so on. But for the most basic one, you just place the value, click outside. Then the easiest way to do it, because your load most likely will start in one phase and carry on on all upcoming phases. So the easiest way to do it is just click final stage, click the beam, click final stage, click the beam, and you finish like quite easily. And then the same for live load. Yeah, we take like 15 and we say okay, but this live load is only active in like final stages, so not an intermediate ones. And then if you want an overview, you can have an overview like this with all the phases and all the loads. And then of course in the load combinations, you can combine them with the appropriate factors, and you can change the safety factors or not. So yeah, 135, I can do it 1.5, I can do it 1.85, so whatever I want, and I just click change. If I don't, if I use different safety factors than what prestress has by default. All right, then I don't know, maybe some of you can use the raise hand. So I will give you like 2 options, and we can, you know, do as much as we can in like 10, 15 minutes max about the design. Would you like to see a design of a hollow core, or a design of, I don't know, a constant beam, or the third option, a sloped beam? So I will say 1 and then raise hand, 2 raise hand for each individual option that I gave you, and then in a democratic fashion we decide which one we do. So let's start. 1, 2, 3. Okay, I don't know if whether yeah, you know how to use this yeah, I see a raised hand. Okay, let me count them down. So we will do a slope tie beam apparently. So yeah, we can go to either do it by start to finish, which I think it will be the best for new and experienced users alike. So let's call it tests 2024. We take a length of 20 meters. We take a slope tie beam. We configure it very, very fast. So 34 meters, no, maybe better like this. And all right, now let's modify this by, let's say 6,000 and 3,000. All right, now that's more likely. And we just leave the sections as they are here. So probably we should reduce a little bit the height. I don't know. Yeah. Okay, this looks like almost something doable. Okay, and then we click the add button, and yeah, we go to directly to the longitudinal reinforcement. So again, something that I found out from my latest call in regards to pre-stress. I had a very demanding customer. I don't know whether he's here or not, but he had a lot of questions, and all of them were actually valid, and it made me realize that something that is so easy or by default for me, it doesn't come so easy when you have your first contact with pre-stress. So one of his questions was in regards to the top reinforcement, and if you look at the section, because it's a sloped beam, it has an inclination, and he actually placed an inclined angle to the top reinforcement. But you don't need to do that, because by just using this layer of reinforcement, for example, I can select 2 bars at the top, right? And I click OK, and you see my bars are following the slope line. So basically, the governing factor for the position of the bar is the concrete coverage. So you just insert the bars, you know, like a number and the diameter, and pre-stress will automatically position them to follow the line, the top line of your beam. Okay, and then let's go to the bottom side and say I want 4 bars and 4 bars. but I don't want them like this. I want my first two bars. In some countries, there is a rule that the first line of bars should be passive. So for those of you, you can still edit the first bar as a wire and then modify it to make it as a passive reinforcement. And the easiest way to do that is, of course, looking in this table. So I have the Z coordinate, and Z is 36. So those four are my first line. And I'm not working on the position. What I do want to work is at the material first. So I do like this. Okay. And I convert them from tendons to passive. And of course, that is not enough. I should do something extra. I think I converted one that wasn't there. Yeah, two. Sorry. Let's convert them back. Okay. All right. So now we have our first 4 bars converted, but we still have a pre-stressing force. So if there are passive reinforcement, we shouldn't have, right? So, okay. And what the software did, it converted my bar to the closest passive reinforcement diameter that they had. And because we use 12.9, it converted to 12 diameter. So we can, you know, like go 16. Okay, and now I think should look okay. Yeah. So now it's what I wanted. The first line is passive reinforcement. Second line is tendons. So we can go in to the stirrups, and let's take the default placing, and we'll take it from there. And yeah, another question. I keep making reference to this call because it's fresh in my mind, and probably his questions are also relevant for you guys. So you see here, I only have like a one leg stirrup. So what I can do, if, for example, I want to disregard the fact that pre-stress takes into consideration the fact that you need a certain thickness for the concrete vibrator to go to be able to go in and vibrate the element. So if you know you have like a mold vibrator and you want to do something like a 2-leg stirrup, how you do that? Well, it's easy. You just cut the distance in half, because basically you have a certain distance in which the shear force is being calculated, and the shear plane intersects a number of legs, right? So if you would have had like 2-leg stirrups, let's say if you have a distance of I don't know, 100, and your shear distance is like 200, normally it will intersect, if you, let's say 350, right, and we place it right in the middle, then it's three stirrups multiplied by 2 is 6, so 6 legs. So what you can do is cut that distance in half. So basically you can do that here. So if you want a double leg stirrup, you just click 150, right? And the same, following the same principle here, it's 50. So that's how you do it. Okay. What else? So yeah, and now we should basically declare our load cases. and yeah, try and see whether we can do a quick design. I will try to be as quick as I can. I don't know, I'm just placing random values at this point, so it might be that it's too low, or it might be that it's too high. I have no idea until we analyze it. So let's place here 15. Yeah. One more thing for the new guys is the exposure class and the strength class. And it's, yeah, I always say this. This is very important, both of them. So basically, prestressed takes into consideration the evolution of concrete in time. So of course, when you demold your element, it hasn't reached his full class, his final class. So in this, by default value, in this particular example, it starts from a C30 and it develops in the storage and maturing up till a C40 in the transport stage. And yeah, the exposure class, you should select the appropriate exposure class. All right, then yeah, moving back, let's do like this. Okay, so we have made like our load combinations. Let's see the calculation. Invalid cover, so it gives me a warning in regards to concrete coverage. I can choose to respect that, going back and correct it, or I can choose to ignore it. That's up to the engineer. So normally, yeah, you should respect your concrete coverage. Sorry. It takes a little bit. I don't know if whether we have made like a correct design or completely fantasy one. Yeah. We will see in a minute. It usually goes slower when you share your screen. I don't know why. Probably has to do something with the backend. All right, so we have our initial results. Now let's see the code control. And then we decide together how far are we from an optimal design or not. Again, I received like, yeah, current stirrups are less than required minimum reinforcement and fail to achieve convergence in trying to determine the moment capacity. So not as we expected. It's a flawed design, of course, and it's a fantasy academic model. But when you are designing your beam, it basically follows the same flow. It's just that, yeah, yours will probably look better than this one, as it is a realistic project, right? So as I see, we start to have problems in the intermediate stage. So let's see what's up. Yeah, so the crack weight control. Then let's see, how are we? Oh, compression stress. Yeah, so as suspected, we have very few reinforcement inside, and yeah, you see here it's like 2.2, so it's 120 exceeded the maximum value. So yeah, normally what we do now is we go back to the beginning and we modify our project, and you know, we add more reinforcement, and maybe we do like yeah, we leave the first 4 alone, and we do something like this. Maybe this is overkill, but yeah. So this is how you basically follow the design of a sloped I-beam. It follows the same pattern as a constant beam, with the only difference that yeah, when you do the initial input for this one, you have a little bit more to configure in terms of yeah, the geometry. Other than that, the flow is identical. So thank you all for participating. As I said in the beginning, I will answer your questions through email. And yeah, if there are like people that want a more in-depth view for prestress, and they are interested to acquire software like this, we can even book a one-on-one call, and I will gladly show you everything about prestress that I didn't manage to do in this webinar. So thanks again, and have a good day. Bye-bye.